Welcome to Lecture 29. We're going to pick up where we left off with our discussion of gravity. Last time I asked you to think about gravity in terms of a gravitational field. And this is the point of view, essentially, of Einstein's theory of relativity. So I mentioned last time something about massive objects warping space-time. And that's essentially what Einstein's theory of general relativity tells us. That what happens is that the gravitational field is warping space-time, the space and time in which the mass is embedded. And so you can think about that as the mechanism for this sort of gravitational attraction of massive objects. And what's more is that while this allows for the acceleration due to this force of attraction to take place, that acceleration due to the gravitational field is essentially indistinguishable from acceleration due to some uniform linear acceleration. So no experiment that you attempt to perform could tell the difference between a gravitational acceleration and some uniform linear acceleration of the same magnitude. So a little thought experiment, as Einstein was fond of using, would be to picture Emmy Noether, who helped Einstein with a lot of the mathematics of his theory of relativity, in two different situations. One is where she is enclosed inside of a crate sitting on the surface of the earth. Inside of this crate with no windows, everything behaves as would be expected on the surface of the earth. If she drops the ball, it will accelerate at 9.8 meters per second squared. She feels a normal weight that she's used to feeling. But if we put Emmy Noether instead into some other crate, which is accelerating upward at 9.8 meters per second squared, there would be no way for Emmy to distinguish that she's not, in fact, sitting on the surface of the earth. If she drops the ball, it will accelerate downward at 9.8 meters per second squared just the same way it would on Earth. Her weight would seem the same. Everything would seem as though she were sitting on the earth. So one application of this fact is that, in principle, space travelers could exploit this to have some sort of artificial gravity, and effectively the effects of weightlessness would be mitigated because their body would behave as if it's in the gravitational field of the earth. You wouldn't suffer that sort of muscle atrophy and bone loss that plagues astronauts in microgravity. So let's talk about the implications of Einstein's theory of general relativity. First of all, we have concluded that what's happening with these massive objects is that the space-time around them is being warped. Okay, this is often the kind of cartoon that's been being shown to illustrate this. Of course, this is treating it as though it's a two-dimensional problem. In reality, it's a three-dimensional problem, but you get the picture of how the space-time fabric, so to speak, is indented near the presence of anything massive. And so some of the predictions of general relativity and the fact that space-time is warped in this way can be seen as follows. So first of all, light will travel along the fabric of space-time. So if space-time is indented and curved near the presence of something massive, then light will take on a curved trajectory instead of a straight trajectory. What happens then is that if we were, say, on Earth and looking out into the sky and saw a star, we would assume that it followed some straight line trajectory. It would appear as though, connecting the dots, it's at this particular position, when in fact it may be coming from behind the sun because of the light that had to be warped near the sun. Well, what's the problem with trying to see if this is the case? Well, generally you're not going to see some distant star in the glare of the sun if you look near the vicinity of the sun. So the only time that you can do this sort of observation is during a total eclipse of the sun. And of course, by the way, if you are trying to observe a total eclipse of the sun, please make sure you take precautions to do so indirectly, as it can cause eye damage. But with that disclaimer out of the way, Einstein came up with his theory of general relativity in 1915, and it so happened that there was a total solar eclipse in 1919. And based upon the prediction that the apparent position should differ from the actual position of any stars near the sun, people took to looking for this effect and were able to actually verify that the known distance or the known position of a certain star was off from its apparent position during the solar eclipse, where the light was warped near the presence of the sun. Other effects that show that this idea of warping of space-time is correct include something that is called the Einstein's cross, or any kind of optical effect like this, in which some sort of foreground massive object, such as a large galaxy, lenses, quote unquote, something in the background. And this can either bring the thing into focus or produce copies of it on either side of the foreground massive object. And this is seen telescopically in many of the Hubble images, for example. Another verification of this warping of space-time is in the precession of Mercury's orbit. The precession of Mercury's orbit was known and remained a mystery, but it made sense in terms of this warping of space-time, because when Mercury goes around the sun here, it's sort of going downhill, quote unquote, and then it has to come back uphill, so it sort of loses steam and ends up tracing out this precessed orbital pattern that looks more like a spirograph than some sort of regular ellipse. And if you still don't believe that this is the case, consider that even the Earth itself warps space-time because of its own mass, and all of our GPS and satellites have to make corrections for this to give us accurate information. So every time you use your GPS on your phone, it is making corrections for the fact that the space-time near the Earth is warped. All right, so let's talk about something that students find even more interesting, generally speaking, and recall that there was something that we derived in the previous lecture called escape velocity, which told us how fast we need to send some sort of spacecraft or any sort of object leaving our Earth in order to escape its gravity and be able to go off and not return. And we said that formula for finding this on any massive world would be the square root of 2g times the mass of the world divided by r. Well, another part of Einstein's relativity harkens back to 1905 with his special relativity, in which it became understood that nothing in the universe can travel faster than the speed of light. So what if we set this left-hand side equal to the speed of light? If this left-hand side of the equation is equal to the speed of light, then the escape speed is the speed of light. Anything greater than that, and nothing can escape, not even light. And this is exactly what happens in what we call a black hole. You have so much mass compacted into such a small radius that this number becomes so large that even light cannot escape, nothing can escape. So you can picture this like so. If you have a normal star and you're trying to escape, you go the escape velocity. When you have a neutron star, it's very hard to get out of that gravitational field, but perhaps you can make it. But if you have something even more compact and massive, it will always just turn back in onto itself. There is no way to actually escape this gravitational field. Finally, another prediction made by the theory of general relativity is gravitational waves. So if we are to picture what's going on in 3 dimensions, whenever something massive is warping space-time, it's also sort of dragging things along and producing ripples if there are 2 massive objects near each other and they're interacting in this way. These ripples should propagate through the fabric of space-time and in principle be detectable. Of course, you need something rather massive to produce enough of a gravitational wave to be detectable, but that's exactly what the LIGO detector was designed to do. And LIGO in 2015 is when it began operating, and shortly thereafter was able to find gravitational waves. You can explore these links to see more about that. But basically, LIGO was able to discover gravitational waves from merging black holes, and this discovery of gravitational waves was a Nobel Prize winning discovery. In our next lecture, we will discuss one more example related to gravitation, and that will finish up Unit 8.